Weighing scales are devices to measure weight or calculate mass. Spring balances. A spring scales measure weight by balancing the force due to gravity against the force on a spring, whereas a balance a pair of scales using a balance beam compares masses by balancing the weight due to the mass of an object against the weight of a known mass or masses. Either type can be calibrated to read in units of force such as newtons, or in units of mass such as kilograms, but the balance a pair of scales using a traditional balance beam to compare masses will read correctly for mass even if moved to a place with a different gravitational field strength, while the spring balance would read correctly in force in a different gravitational field strength. Force measuring scales. History. Although records dating to the 1700s refer to spring scales for measuring weight, the earliest design for such a device dates to 1770 and credits Richard Salter, an early scale maker. Spring scales came into wide usage in the United Kingdom after 1840 when R. W. Winfield developed the candlestick scale for weighing letters and packages, required after the introduction of the uniform penny post. Postal workers could work more quickly with spring scales than balance scales because they could be read instantaneously and did not have to be carefully balanced with each measurement. By the 1940s, various electronic devices were being attached to these designs to make readings more accurate. Load cells, small nodes that convert pressure to a digital signal, have the beginnings as early as the late 19th century, but it was not until the late 20th century that they became accurate enough for widespread usage. Mechanical scales. Spring scales. A spring scale measures weight by reporting the distance that a spring deflects under a load. This contrasts to a balance, which compares the torque on the arm due to a sample weight to the torque on the arm due to a standard reference weight using a horizontal lever. Spring scales measure force, which is the tension force of constraint acting on an object, opposing the local force of gravity. They are usually calibrated so that measured force translates to mass at Earth's gravity. The object to be weighed can be simply hung from the spring or set on a pivot and bearing platform. In a spring scale, the spring either stretches or compresses. By Hooke's law, every spring has a proportionality constant that relates how hard it is pulled to how far it stretches. Weighing scales use a spring with a known spring constant and measure the displacement of the spring by any variety of mechanisms to produce an estimate of the gravitational force applied by the object. Rack and pinion mechanisms are often used to convert the linear spring motion to a dial reading. Spring scales have two sources of error that balances do not. The measured weight varies with the strength of the local gravitational force, and the elasticity of the measurement spring can vary slightly with temperature. With proper manufacturing and setup, however, spring scales can be rated as legal for commerce. To remove the temperature error, a commerce legal spring scale must either have temperature compensated springs or be used at a fairly constant temperature. To eliminate the effect of gravity variations, a commerce legal spring scale must be calibrated where it is used. Hydraulic and pneumatic scale. It is also common in high-capacity applications such as crane scales to use hydraulic force to sense weight. The test force is applied to a piston or diaphragm and transmitted through hydraulic lines to a dial indicator based on a board and tube or electronic sensor. Digital scales. Digital bathroom scale. A digital bathroom scale is a type of electronic weighing machine which is used to measure many readings including body fat, BMI, lean mass, muscle mass, water ratio along with body weight. The digital bathroom scale is a smart scale which has many functions like smartphone integration, cloud storage, fitness tracking, etc. MJ mjh strain gauge scale. In electronic versions of spring scales, the deflection of a beam supporting the unknown weight is measured using a strain gauge, which is a length-sensitive electrical resistance. The capacity of such devices is only limited by the resistance of the beam to deflection. The results from several supporting locations may be added electronically, so this technique is suitable for determining the weight of very heavy objects, such as trucks and rail cars, and is used in a modern weigh bridge, supermarket and other retail scale. These scales are used in the modern bakery, grocery, delicatessen, seafood, meat produce and other perishable goods departments. Supermarket scalies can print labels and receipts, mark weight, count, unit price, total price, and in some cases dare. Some modern supermarket scalies print an RFID tag that can be used to track the item for tampering or returns. Weighting scale in retail saves time inputting a lot of product information using management program, entering every menu mode using shortcut keys. In most cases, these types of scales have a sealed calibration so that the reading on the display is correct and cannot be tampered with. In the USA, the scales are certified by the National Conference on Weights and Measures (NTEP). In South Africa by the South African Bureau of Standards, and in the UK by the International Organization of Legal Metrology. Testing and certification. Most countries regulate the design and servicing of scales used for commerce. This has tended to cause scale technology to lag behind other technologies because expensive regulatory hurdles are involved in introducing new designs. Nevertheless, there has been a recent trend to digital load cells, which are actually strain gauge cells with dedicated analog converters and networking built into the cell itself. Such designs have reduced the service problems inherent with combining and transmitting a number of 20 mV signals in hostile environments. Government regulation generally requires periodic inspections by licensed technicians using weights whose calibration is traceable to an approved laboratory. Scales intended for non-trade use, such as those used in bathrooms, doctors' offices, kitchens, and price estimation, may be produced, but must by law be labeled "not legal for trade" to ensure that they are not repurposed in a way that jeopardizes commercial interest. In the United States, the document describing how scales must be designed, installed, and used for commercial purposes is NIST Handbook 44. Legal for trade certification usually approve the readability as repeatability, tend to ensure a maximum margin of error of 10%, because gravity varies by over 0.5% over the surface of the Earth. The distinction between force due to gravity and mass is relevant for accurate calibration of scales for commercial purposes. Usually the goal is to measure the mass of the sample rather than its force due to gravity at the particular location. Traditional mechanical balance beam scales intrinsically measured mass, but ordinary electronic scales intrinsically measure the gravitational force between the sample and the Earth, i.e., the weight of the sample, which varies with location, so such a scale has to be recalibrated after installation for that specific location, in order to obtain an accurate indication of mass. Sources of error. Some of the sources of error in weighing are buoyancy. Objects in air develop a buoyancy force that is directly proportional to the volume of air displaced. The difference in density of air due to barometric pressure and temperature creates errors. Error in massive reference weight. Air gusts, even small ones, which push the scale up or down. Friction in the moving components that causes the scale to reach equilibrium at a different configuration than a frictionless equilibrium should occur. Settling airborne dust contributing to the weight. miscalibration over time, due to drift in the circuit's accuracy, or temperature change, misaligned mechanical components due to thermal expansion or contraction of components, magnetic fields acting on ferrous components, forces from electrostatic fields, for example, from feet shuffled on carpets on a dry day, chemical reactivity between air and the substance being weighed, condensation of atmospheric water on cold items, evaporation of water from wet items, convection of air from hot or cold items, gravitational differences for a scale which measures force but not for a balance, vibration and seismic disturbances. Balance scales. The original form of a balance consisted of a beam with a fulcrum at its center. For highest accuracy, the fulcrum would consist of a sharp V-shaped pivot seated in a shallower V-shaped bearing. To determine the mass of the object, a combination of reference masses was hung on one end of the beam while the object of unknown mass was hung on the other end. For high-precision work, such as empirical chemistry, the centerbeam balance is still one of the most accurate technologies available, and is commonly used for calibrating test weights. Mechanical balances. The balance was the first mass-measuring instrument invented. In its traditional form, it consists of a pivoted horizontal lever with arms of equal length, the beam, and a weighing pan suspended from each arm. The unknown mass is placed in one pan and standard masses of known weight are added to the other pan until the beam is as close to equilibrium as possible. In precision balances, a more accurate determination of the mass is given by the position of a sliding mass moved along a graduated scale. Technically, a balance compares weight rather than mass, but, in a given gravitational field, the weight of an object is proportional to its mass. So the standard weights used with balances are usually labeled in units of mass. Unlike spring-based scales, balances are used for the precision measurement of mass, as their accuracy is not affected by variations in the local gravitational field. A change in the strength of the gravitational field caused by moving the balance will not change the measured mass, because the moments of force on either side of the beam are affected equally. A balance will render an accurate measurement of mass at any location experiencing a constant gravity or acceleration. Very precise measurements are achieved by ensuring that the balance's fulcrum is essentially friction-free, by attaching a pointer to the beam which amplifies any deviation from a balance position, and finally by using the lever principle, which allows fractional masses to be applied by movement of a small mass along the measuring arm of the beam, as described above. For greatest accuracy, there needs to be an allowance for the buoyancy in air, whose effect depends on the densities of the masses involved. To reduce the need for large reference masses, an off-center beam can be used. A balance with an off-center beam can be almost as accurate as a scale with a center beam, but the off-center beam requires special reference masses and cannot be intrinsically checked for accuracy by simply swapping the contents of the pans as a center beam balance can. To reduce the need for small graduated reference masses, a sliding weight called a poise can be installed so that it can be positioned along a calibrated scale. A poise adds further intricacies to the calibration procedure, since the exact mass of the poise must be adjusted to the exact lever ratio of the beam. For greater convenience in placing large and awkward loads, a platform can be floated on a cantilever beam system which brings the proportional force to a nose iron bearing. This pulls on a still yard rod to transmit the reduced force to a conveniently sized beam. One still sees this design in portable beam balances of 500 kilograms capacity, which are commonly used in harsh environments without electricity, as well as in the lighter-duty mechanical bathroom scale. The additional pivots and bearings all reduce the accuracy and complicate calibration. The float system must be corrected for corner errors before The span is corrected by adjusting the balance beam and poise. Roberval balance. In 1669, the Frenchman Gilles Person de Roberval presented a new kind of balance scale to the French Academy of Sciences. This scale consisted of a pair of vertical columns separated by a pair of equal-length arms and pivoting in the center of each arm from a central, vertical column, creating a parallelogram. From the side of each vertical column a peg extended. To the amazement of observers, no matter where Roberval hung to equal weight along the peg, the scale still balanced. In this sense the scale was revolutionary. It evolved into the more commonly encountered form consisting of two pans placed on vertical column located above the fulcrum and the parallelogram below them. No matter where equal weights are placed in the pans, the scale will still balance. Further developments have included a gear balance, in which the parallelogram is replaced by any odd number of interlocking gears greater than 1, with alternating gears of the same size and with the central gear fixed to a stand and the inert side gears fixed pans, as well as the sprocket gear balance, consisting of a bicycle-type chain looped around an odd number of sprockets with a central one fixed and the outermost two free to pivot and attach to a pan. For reasons involving friction and tension, the Roberval balance is consistently less accurate than the traditional beam balance, but for many purposes this is compensated for by usability. Electronic devices. Microbalance. A microbalance is an instrument capable of making precise measurements of weight of objects of relatively small mass, of the order of 1,000,000 parts of a gram. Analytical balance. An analytical balance is a class of balance designed to measure small mass in the sub-milligram range. The measuring pan of an analytical balance is inside a transparent enclosure with doors so that dust does not collect and so any air currents in the room do not affect the balance's operation. This enclosure is often called a draft shield. The use of a mechanically vented balance safety enclosure, which has uniquely designed acrylic airfoils, allows the smooth turbulence-free airflow that prevents balance fluctuation and the measure of mass down to 1 microgram without fluctuations or loss of product. Also, the sample must be at room temperature to prevent natural convection from forming air currents inside the enclosure from causing an error in reading. Single pan mechanical substitution balance maintains consistent response throughout. The useful capacity is achieved by maintaining a constant load on the balance beam, thus the fulcrum, by subtracting mass on the same side of the beam to which the sample is added. Electronic analytical scales measure the force needed to counter the mass being measured rather than using actual masses. As such, they must have calibration adjustments made to compensate for gravitational differences. They use an electromagnet to generate a force to counter the sample being measured and outputs the result by measuring the force needed to achieve balance. Such measurement device is called electromagnetic force restoration sensor. Pendulum balance scales. Pendulum-type scales do not use springs. This design uses pendulums and operates as a balance and is unaffected by differences in gravity. An example of application of this design are scales made by the Toledo Scale Company. Symbolism. The scales are one of the traditional symbols of justice, as wielded by statues of Lady Justice. This corresponds to the use in metaphor of matters being held in the balance. It has its origins in ancient Egypt. Scales are also the symbol for the astrological sign Libra. History of the balance scale. The balance scale is such a simple device that its usage likely far predates the evidence. What has allowed archaeologists to link artifacts to weighing scales of the stones for determining absolute weight. The balance scale itself was probably used to determine relative weight long before absolute weight. The oldest evidence for the existence of weighing scales dates to c. 2400 or 1800 BC in the Indus River Valley. Prior to that, no banking was performed due to lack of scales. Uniform, polished stone cubes discovered in early settlements were probably used as weight-setting stones in balance scales. Although the cubes bear no markings, the weights are multiples of a common denominator. The cubes are made of many different kinds of stones with varying densities. Clearly the weight, not the size or other characteristics, was a factor in sculpting these cubes. In Egypt, scales can be traced to around 1878 BC, but the usage probably extends much earlier. Carved stones bearing marks denoting weight and the Egyptian hieroglyphic symbol for gold have been discovered, which suggests that Egyptian merchants had been using an established system of weight measurement to catalogue gold shipments and/or gold mine yields. Although no actual scales from this era have survived, many sets of weighing stones as well as murals depicting the use of balance scales suggest widespread usage. Variations on the balance scale, including devices like the cheap and inaccurate Bismarck, began to see common usage by c. 400 BC by many small merchants and their customers. A plethora of scale varieties, each boasting advantages and improvements over one another, appear throughout recorded history, with such great inventors as Leonardo da Vinci lending a personal hand in the development. Even with all the advances in weighing scale design and development, all scales until the 17th century AD were variations on the balance scale. Hybrid spring and balance scales. Elastica arm scale. In 2014, a concept of hybrid scale has been introduced, the elastically deformable arm scale, which is a combination between a spring scale and a beam balance, exploiting simultaneously both principles of equilibrium and deformation. In this scale, the rigid arms of a classical beam balance are replaced with a flexible elastic rod in an inclined frictionless sliding sleeve. The rod can reach a unique free of sliding equilibrium when two vertical dead loads are applied at its edges. Equilibrium, which would be impossible with rigid arms, is guaranteed because configurational forces develop at the two edges of the sleeve as a consequence of both the free sliding condition and the nonlinear kinematics of the elastic rod. This weight measuring device can also work without a counterweight.